PET using an ionic liquid derived from 1,3-dimethyl-imidazolium 2-carboxylate organocatalyst. Please welcome.
Thank you. I'm not sure how to respond to that really nice welcome. Okay, that's great. So thank you everyone for the invitation to speak at your meeting, and it's actually nice to see familiar faces in the audience as well. I'm looking at the attendance list. What I'm going to hope to do is tell you a little bit about work and a bit about a pathway that we've been going through for a number of years in our research, or my research, both in Alabama at certain points and especially now at Queen's University in Belfast. And I really want to try and motivate everyone a little bit by showing how looking at fundamental chemistry can lead to unexpected results and unexpected areas of opportunities for applications and advancements, especially in the context of this meeting, in addressing or potentially addressing climate change. And I want to hope at the end to really discuss and show you where aspects of the chemistry can lead to impacts across a broad range of areas. So not necessarily looking specifically at the science we're talking about here, but how it impacts across that broad range of changing chemistry, but also impacting in lowering our carbon footprint through how that can change engineering as well. So I think it's really important for us as chemists especially to be quite holistic about this. So thank you. The first of these slides is where we start. And actually, I'm not that old. We started off one aspect of work being wanting to look at using the technology we look at ionic liquids to change how we treat and use biomass, in particular, try to have ways of looking at cellulose processing to try and get to rayon and cellophane and cellulosic wrappers. And we were inspired by work from the 1930s in Switzerland using pyridinium salts as alternatives to the xanthate process for dissolving cellulose. So you notice this was using a pyridinium salt which melted at about 150 degrees. If we can move on, next slide. What we developed and what we looked at was seeing if we can use more conventional, at least by the 2000s, more conventional ionic liquids, particularly imidazolium salts, to do the same work. And of course, we have a very well-cited and well-recognized piece of work in this area, identifying that imidazolium halide ionic liquids are very good solvents to cellulose. And this led to a lot of effort to see whether this could be commercialized and used in an effective way. If you look at the next slide, you can see that the idea is very simple, and we like simple ideas. We could take crystalline or microcrystalline cellulose, dissolve it very rapidly with ionic liquids, and then regenerate this to form fibers or beads or films through normal technology of processing by recoagulation, reprecipitation in water, and then recover and recycle the ionic liquid. And this is the model that we had, and we developed demonstrations of how to do this. Let's go next. Perfect. Next slide. As researchers, as chemists in academic labs, we're not always very well prepared to fully develop and exploit technologies. So this was research that was moved and sub-licensed to BASF as one of the biggest chemical companies in the world to see if they could do more with it. And they, of course, put a lot of people onto this and screened a whole load of ionic liquids. And what they identified from a massive amount of work was that ethyl methylimidazolium acetate was identified as a good solvent for cellulose dissolution. So I've got it highlighted there. And this led in the next slide to them trying to develop technologies based on that. But I guess as chemists, we should have realized that there were some unexpected consequences from this. And I want to highlight this because this leads us into what we're doing now. One of the unexpected consequences is that you can use imidazolium salts in the presence of base. And the acetate anion that was used is, of course, quite basic to generate N-heterocyclic carbenes, which can be used for a whole host of different chemistry. And why I say this is an unexpected consequence that we should have known was that Anthony Arduino was on the previous slide. I guess this is changing on its own. Was actually at the other end of the corridor from us at the University of Alabama while we were doing the work. And he had worked at DuPont in developing the classic work on these carbenes. So I guess we should have known by realizing what our colleagues were doing that this might have happened. If you move on to the next slide, this is recognized and is utilized now, and here's a beautiful piece of work from Professor Tom Welton at the University College London, sorry, in Imperial College London, he'll kill me for that, utilizing the presence of carbenes in ionic liquids during the dissolution of cellulose to recognize how this can induce chemical reactions. So really what I say is there's a lot of unexpected consequences come out of needing to know what's happening in the chemistry you're doing. And in this case, it's the generation of carbenes. Let's look at how these carbenes do something with PET here. So what we're interested in now is looking at polyethyl terephthalate waste. So waste plastic bottles, waste clothing. And we want to look at the recycling of it to try and improve on or to complement the physical recycling that can be done by just simply melting and reprocessing these materials. So next slide. So this is a schematic which actually I'm using teaching to our chemical engineers about the concept of integrating chemical recycling, which we can see here, I guess. Do I have a, no, I don't have a pointer. Chemical recycling into mechanical recycling to try and recover both energy and resources from, in this case, waste plastics as part of a circular economy approach, which of course is what we want to do. Let's look at what we're trying to do. The next slide. So what I want to show you today is work here that we've been doing on, let's say, on recycling of polyester by glycolysis using an ionic liquid derived catalyst, and I'm going to show you how this can actually lead to some advances. There's our beautiful picture. That was the graphical abstract for the paper. We want to look at this glycolysis with PET. Can I get the next slide? So the idea is that this is one of the primary feedstocks for the petrochemical industry, and what we're trying to address really is how we can get away from using petrochemical resources to reduce our chemical footprint, our demand on things, and actually potentially more than anything else try to maximize the use of petrochemical resources for useful things other than necessarily as fuels, which will lead to our carbon emissions and things like that. And the recognition that we teach is that most of our chemicals come from these primary chemical resources. And to that, really, I want to highlight here ethane C2 and xylene C8 fragments, which do lead directly to polyester manufacturing at a massive scale. I've got some noted figures, which are actually a bit out of date now, but US chemical production was in the order of 300 million tons a year, of which of that, something like 120 million tons a year is to generate chemicals and polymers, and polyester is a major contribution to that. Can we look at the next slide? And you can see very easily how it's done, and this is, for the engineering side of people in the audience. The process of doing terephthalic acid is to take terephthalic acid and ethylene glycol, to heat them and dehydrate them over normally an antimony catalyst, removing the water. It's a very simple integrated process. The next slide, please. And as you can see, it is a beautiful and very much a vertical process that works well within the within the petrochemical industry. You can go directly through from crude oil through production of xylenes, generation of polyethylene glycol from ethylene to make the polyesters. What we're trying to do, and what we're going to look at in the research, next slide please, is how we can break out of that petrochemical approach and get something useful, I hope. So, and this is my justification, this is my pitch, if you like, though we're kind of halfway through. Over 50, probably close to 70 million tons of polyester produced every year at the moment, used for everything. Most visible aspect probably is plastic bottles, drinks bottles, and the value of the resin for this is high, which justifies why it is worth recycling it rather than just burning it as a energy resource, as a waste product. But I would note, and let's get to the next slide, that what's really important is that though we can regenerate this physically by melting and reprocessing, that does lead to impurities and ultimately to weakening. And the reality is that most recycling of polyester, as you note here on this slide, this is actually done about 10 years ago, it's recycled and generates what's called fiber. This makes things like carpet tiles, thermal fleeces, things like that. So it's not being kept within its primary use for packaging, for bottles, for high performance uses of the polyester itself. So what we're trying to introduce with our chemistry here is to take the polymer and break it from this. This is my representation of polymer using Lego. The polymer made of component units, and break them down in chemical terms into its component units, which is next slide, like this, so that we can take our chemical units perfect and regenerate them and build up the polymer again. Because once we've got, from a chemistry perspective, from those chemical subunits, they're chemically identical to those that we generated from the petrochemical process in the first place. So our role as chemists in recycling is to try and get chemicals which are identical to the things that we started with. Okay, next slide as well. This is the strategy. Let's go to the next one. And the next one. That's it. What we're going to look at is glycolysis. The approach of taking polyester, this polymeric ester of terephthalic acid, and we're going to add to it ethylene glycol. And in doing so, if we can crack the ester, a straight, simple chemical reaction, we can make what's called B-het, which is actually the first intermediate in the polymerization process. So we're breaking this down into components that can go straight back into the polymer food chain. If you look at the chemistry of this, there's a wide range of catalysts that have been studied, and I've got a bucket list there of things. Most interesting things are metal acetates, really, and I'll highlight some use of those in a second. But also I would note here that in current research, ionic liquids have been looked at, and carbene catalysts. Excuse me, I really do have to pause for a minute. Sorry. So we're talking about trying to crack the polyester this way, and we can use a wide range of catalysts. Next slide, please. And as I say, the most common thing is zinc acetate. Please bear in mind the results that we got on there. Without the catalyst, we just heat the polymer at 190 degrees. Eventually, after about 6 to 7 hours, you do get cracking. We do get deesterification and production of monomer. In the presence of zinc acetate, after about 30 to 40 minutes, we can get about 60% yield conversion to the B-het. And this, if you like, is probably industry standard. This is as good as you normally get, and it works perfectly well. 1% zinc acetate as a catalyst. Let's move to the next slide, because we're not interested in terms of ionic liquid research in zinc acetate. We're really interested in trying to see what we can do with our materials. And of course, we're not the only people who've been looking at this. If you send the students to look in the literature, they find that there's lots of research going on looking at potential to use things like ionic liquids as catalysts to induce esterification, transesterification reactions. And I've just cherry-picked some very good work there, especially from Suzanne Zhang's group in Beijing, on looking at the uses of a range of ionic liquids, particularly containing metals, which are analogous, if you like, to the zinc acetate as catalysts for this. They're very good, they do work, but we are asking, can we do better? So next slide. Let me just jump through this. And what we noted, and I want to lead you through to where we can get with this quite quickly. What we noted is actually using one of our old friends, imidazolium acetate ionic liquid, one of the materials that we were looking at and BASF were looking at for cellulose production. This could be used, and it was reported that this gave, I've highlighted in the box there, relatively good conversion. This group could actually get up to about 50% yield and about 75% conversion of polyester to product using the ionic liquid as a catalyst. Now, this might be ringing bells from the start of what I said, 15 minutes ago, that you could generate carbenes as we saw, or as Tom Wells and other people saw with imidazolium acetates, with looking at cellulose, with this ionic liquid. And indeed, it was speculated that formation of an N-heterocyclic carbene from this ionic liquid could be driving the mechanism for this catalysis to get this material. But it's interesting because it doesn't contain a metal. So there's an opportunity there to change the catalytic process. Let's look at the next slide, move on. I'm going to note, because we're trying to do a bit of a literature survey as we go through this, that using N-heterocyclic carbenes as catalysts for esterification chemistry, both to making esters and doing trans-esterification, was already known and had been identified for a range of reactions, including making things like polylactide from PLA, so quite green renewable polymer sources can be made with using these carbene catalysts to drive the reaction. And also, I'm going to note in highlighting this box, it's really good from Lefebvre's work, that they looked to identify using trans-esterifications using both imidazolium carbonate catalysts and also this material there, number 3, a carboxylate, as a precursor to carbenes. Let's look at the next slide. This sparked our interest because we'd looked a long time ago about making the zwitterion, actually for completely different reasons. But as we know, it is being used as a source of CO2 protected carbene to deliver carbenes as reactive species. So we tried to look at this and said, okay, can we use this material that we've got in the lab that we've looked at quite a lot as a precursor to do the same chemistry that's been seen with the ionic liquids as interesting catalysts? So let's go a bit further forward. Let's next slide. And I'm going to skip a few things here. So again, the next slide. And there's the time. This is the key point, is we have on the left here an imidazolium cation, which has got the potential in the presence of base to make carbene. And the carbene has been implicated as a very good basic catalyst for a lot of reactions, including their esterification. On the right, we've got the zwitterionic carboxylate salt, this carbene that's protected by CO2. And if you decarboxylate that, you can also form the carbene. So the interrelation between these two species, both of which could form and react to generate a reactive organocatalyst. Next slide. I want to show a few results, but nothing really too much. This is what we did. We tried to take both on the left and on the right the imidazolium salt and the carboxylate zwitterion and compare them both as catalysts for this reaction, which is taking polyester PET, and it's actually chopped up Coca-Cola bottles. There are other bottles available, and doing this reaction. And we can do that reaction and we can generate at the bottom. It's not come out very well, but a beautiful white crystalline BHET material, which can then be recycled and reused to make more polyester. So it works well. Let's look at the next slide. And here's the data we get. Well, what's really was interesting and amazing to us was that using the carboxylate, the zwitterion, which is the blue line up here, we can see at any reaction we try, at any temperature or at any rate of time, the conversion was a lot faster and a lot more effective than it was with the acetate salt. So that's our take-home message. Okay, next slide. I think that's what. This zwitterion is a much better organocatalyst than the imidazolium salt. We presume, and it's going to take more work to look at mechanisms, that both of these can generate the N-heterocyclic carbene as our reactive intermediate, and that's the actual catalytic species. So the presumption is that the carboxylate can generate the carbene more effectively, more rapidly, and therefore lead to quite remarkable levels of conversion of PET to BHET as intermediate. Okay, next slide. Next slide. I've just talked about this. Is it much better? Yes, it is. Should we use this for certainty? Let's just stop there. Next slide. So I'm going to say we've got this opportunity. We've got a catalyst that works. Is it worth using properly? Well, this is the interesting point. I just want to leave you to think about this. If you go back to 2010, Journal of Chemical Education, so looking at the educational literature, there was a really nice article by Neil Camber on generating an N-cyclic carbene under anhydrous conditions in THF, so classic carbene chemistry, and demonstrating this in an undergraduate organic chemistry lab to do PT cracking to BHET. This is very rapid and works at reflux in anhydrous THF. So if you all think about the boiling point of THF, that's about 40, 50 degrees, right? Compared to the 180 degrees that we use commercially to do this. There's our opportunity. Can we learn from the chemistry we're doing? Can people take that chemistry and reduce the operating temperature for this cracking process from 180 degrees, which is commercial at the moment, to something approaching the temperatures that can be done in a lab, but under anhydrous conditions, which are artificial and not realistic. There's a massive thermal window available to improve on the energy savings that have been gained in the chemical engineering side of the process by modifying and identifying the right catalyst for this system. And that's our window of opportunity to try to look at. So what I'm hoping to show, what I hope to show you in this very quick flyby of this, is that there's an opportunity to recycle materials in alternative ways. We've got to learn from the chemistry we're doing and look at it sometimes in different ways, and also perhaps listen to what our colleagues down the corridor are doing as well. If we'd done that 20 years ago, we might have learned a lot more about what we were doing with the cellulose dissolution. But also, I think from a pure chemistry perspective, there's great opportunities for us as chemists to influence on energy savings and controlling, especially carbon emissions, by influencing and improving on the engineering aspects of processes rather than just on changing the activity in the chemistry. And that's a really important area of thing. So that's it. Can I just leave you the last slide? I just want to acknowledge people who actually did the work. So it's not me. It was primarily an MPhil student, Lei Wang, who I really want to highlight there, who drove a lot of this work through a single year master's program. So she was very good at this, and I really want to congratulate her on that. And thank you all for listening. And sorry for the interruptions I've been having while I've been going through this. And if anyone has any questions, I'm quite happy to answer them.
All right. Participants, if you have any question, you may direct your question in the chat box. Yes. Let's wait for some time. Question?
So, Cecilia's asking, what other anions can be used? Well, in terms of the work that other people have looked at, they've tried just about every anion present in the ionic liquid side of things. Certainly, if you use a basic anion like hydroxide, carbonate, acetate, you would infer and induce that it's making an N-cyclic carbene, and then we expect the carbene catalytic route to take place. But also, especially Zhang has looked at chloride, chlorometallate systems, or general organic liquids with metal salts dissolved in there. And then you have to sort of think that there's potential for mechanistically to this act as both a combination of, it's kind of a push-pull mechanism. You need a base, and any anion is going to be slightly basic, but you also probably need a Lewis, some mechanisms also need a bit of a Lewis acid to coordinate on the carbonyl group of the ester to drive the cracking of the ester, just as you would in any esterification and de-esterification reaction. I have to say, trying to understand the results that are in the literature is very difficult, because a lot of papers will say, okay, we tried something and we get a good result. And it seems to be black-white. You either get a good result and you publish it, or you get a poor result and you ignore it or hide it away. And that's unfortunate, because it doesn't really give us, when we're trying to collate the information, understand what's going on, really how to drive things forward. I think what we're trying to identify here is that the carbenes as super bases are definitely very good materials for inducing this sort of catalysis, and we've got a mechanism here to deliver the NHC in a way that makes it reactive. The challenge is to protect that now in its environment, so it's not killed by the presence of water and other things in there. But I think there's great opportunities from that. Okay, there's another question here. Intriguing session. While we know ionic liquids, there's lots of hype. Some of them are costly. How would we, as chemists, enter green recycling rather than burn plastic waste? I think this is really important. Yeah, it's kind of the lowest denominator, isn't it? That we can always burn plastic waste to generate energy. That is the lowest common denominator. I think what we have to realize is that our whole society has been technologically advanced by our knowledge of making composites, and composite materials are really great. Don't get me wrong, I wouldn't like to fly on an airplane which didn't have a composite wings. But at a simpler level, you know, we see in plastics, composites, mixtures which have really great performance, but it really screws up and makes the recycling of them difficult because it puts so much emphasis both on, as we've seen in some of the presentations, separation at the recycling site, being able to identify different polymers. But then if you've got something like clothing, which is a blend of polyester and cotton, recycling of that is almost impossible because you're trying to split out fibers of different polymers from each other. And I think we have to, in some ways, think about educating society to step back a little bit from some of these technological solutions to things that actually overall are better for society, but may not in the short term be quite so benefit. One example that comes from this, I just say, and it is part of this green education, is that we've seen two things. One, Sprite have switched from green plastic bottles to clear plastic bottles. Why? Because it actually makes them easy to recycle, because they don't include the dyes in there, which when they go into a clear plastic recycling blend, contaminate it. That's really good. Has it had any impact on the flavor and the taste of the drink? No. But it's really important that we can, you know, that sort of awareness about the need for recycling has made that change. And it hasn't had an impact on life other than it improves the recycling. Making sure that the tops on plastic bottles are made of the same polymers as the bottle rather than something else means that we're not inducing blends into our mixtures which are difficult to get out of. And these are the things that I think are really important to do and are very simple if we educate at a low level, you know, from school children upwards, that these things can make the difference. Then we can try and solve the problems rather than I'm to making it a sorting issue. And I think we need to be advocates of that, not just of the high technological solutions, but also of the simple things that can be done.
All right, understood. I think that's all from the question from the chat box. And thank you so much, Professor Dr. John Holbrey, for the educative sharing session. Thank you so much.
Thank you very much. And I think your meetings worked very well. I've joined the latter half of it after I woke up. It's a pity I can't be in Malaysia to participate with everyone in person, but you know, that's the way we are at the moment. But I'm really glad to see it working virtually.
Yes, true. The pandemic, very true. Virtually, yes. All right, thank you, Prof, for your educative sharing session. All right.